This project is sponsored by PCBWay. Don't miss the PCBWay Christmas big sales from November 28th to December 31st. Get free Christmas coupons and redeem or check value a promo code. You can also start with PCB order for only $5. Up to 50% off for 3D printing and CNC machining and special sales in PCBWay stores. PCBWay has all the services to create your own project at the best price.
Hello, high voltage power supply is usually understood as a device that is capable of generating a voltage of several kilovolts or even tens and hundreds of kilovolts. Most often these power supplies give a certain voltage at the output. When experimenting with high voltages, we almost always need a variable value of the generated high voltage. There are several ways to achieve this, and in this project I will try to implement and explain all of these ways in one device. Of course, I will try to make the device as simple as possible and at the same time not to use expensive and difficult to find components. Generally, such a device consists of 3 separate parts: an input source of DC voltage, usually a voltage of 10 to 60 volts, and the ability to provide a current of 3 amperes or more. Then the main part, which is a high voltage generator, or rather a driver for driving a high voltage transformer. It is a generator of rectangular signal with a certain frequency and duty cycle, at the output of which there is a power MOSFET mounted on a large heatsink. And at the end, a high voltage flyback transformer that generates the high voltage, which can be DC or AC. In this project I will focus most of my attention on making the driver circuit, which is actually the most complex to make. Let me start by describing the components individually. The heart of the driver circuit is this inexpensive square wave generator with adjustable frequency and duty cycle. This incredibly useful, I also call it magical module, is responsible for the stability and versatility of the entire circuit. For the price of a few dollars we get a pulse generator with adjustable frequencies from 1 Hz to 150 kHz and a duty cycle from 1 to 99%. It even has a small LCD display on which the selected values are displayed. You can notice that I use this small module in a number of my previous projects. It can be powered by a voltage from 3 to 30 volts and the amplitude of the output signal is equal to the supply voltage. Then we have 2 power MOSFETs type IRF3205 connected in parallel and mounted on a large heatsink that provide power to the low impedance primary of the high voltage transformer. Next, 7812 voltage stabilizer, which serves to power the ZK-PP1 module. This stabilizer limits the output rectangular signal to 12 volts in case we use a power supply greater than 15 volts, thereby protecting the gates of the output MOSFETs. At the signal output of the generator has a potentiometer with which the amplitude of the generated signal can be continuously regulated. At the input side of the low voltage source, there is an automatic fuse that trips in event of a driver failure, most likely a burnout of the MOSFETs. And a few optional components that serve for beta monitoring of the device, which are this small volt ammeter at the input, as well an analog instrument for approximate representation of the value of the output high voltage. Now let's see how the device works in real conditions. At the input I initially bring 12 volts and current limiting to 2 amperes. 12 volt, 2 amperes. At the output I connected a flyback transformer from an old CRT monitor on whose core I wound primary consisting of 7 windings. Here we need to experiment because in different models of transformers the number of windings to achieve the highest efficiency is different. Now we activate the power supply and spark should appear on the secondary of transformer. If there is no spark or it is very small and the current does not exceed 2 amperes, the protection does not turn on, we need to choose a different frequency and duty cycle of the generator. In fact, the duty cycle can be in range of 30 to 45% and the frequency from 10 to 30 kHz depending on the model of the high voltage transformer. In this particular case, the hotspot for best efficiency of this Trafo is a frequency of around 15 kHz. 15.5 kHz and 46% duty cycle. About 15 kilovolts, and spark is 2.5 centimeters. Now about the ways for continuous precise regulation of the output high voltage. The first and simplest way is, as you probably guess, by changing the input voltage to power the device. In this case, the generator parameters remain the same, the potentiometer is at maximum, and only the input voltage changes. We will roughly approximate the voltage value by the length of the spark on the secondary of the transformer, and on this relatively precise kilovolt meter. A spark starts to be generated even at less than 7 volts, which is a sign of good tuning and efficiency on the entire system. Let's try. So we have about 1.5 centimeters spark, 1.5 kilovolts, 15 kilovolts, and 6.9 volts, 1.40 amperes. With increasing the input voltage, the length of the generated spark, i.e. the high voltage, also increases. Let's try that situation. About 12 volts. (20 kilovolts), about 2.5 centimeter spark. We'll go to 15 volts. About 30 kilovolts. And spark longer than 3-4 centimeters. the fuse is activated. If we have the opportunity, instead of a laboratory rectifier that contains a switching circuit and is sensitive to high frequency parasitic signals, it is best to use standard transformer with a classic rectifier on which we install Variac. By regulating the primary voltage through the Variac, we also control the value of high voltage. The next, slightly more crude way to regulate is by changing the duty cycle value. In this case, we set the input voltage to the highest previously determined level and change the duty cycle from 10% to 50%. Let's see how that looks like in reality. At 10% duty cycle, the spark is small, about 1 centimeter, and now I will change duty cycle to another bigger value, and as we see, the spark is much bigger. And vice versa. At 10%, spark is about 1 centimeter. Now spark is about 6 centimeters. And finally, with the potentiometer at the output of the signal generator, that changes the amplitude of the rectangular signal. By moving the potentiometer clockwise, the output high voltage increases proportionally. Let's see how it looks in reality. I thought it would be ideal if we have some kind of visual approximation of the value of the high voltage. So I tried to make a cheap monitor with a small analog instrument. Immediately next to the primary of the high voltage transformer, I wound several turns of insulated wire with diameter of about 0.5 mm, and then through a rectifier and 5 to 10 kilo ohms potentiometer, I brought the ends to the analog meter, in my case with range of 0 to 5 volts. The original primary windings, when working, creates a magnetic flux through the core, whereby the voltage induced in the secondary winding and this additional feedback winding is proportional to the strength of the magnetic flux. In this way, by measuring the voltage generated on the feedback windings, we relatively accurately determine the voltage induced in the secondary winding, that is the high voltage. I don't have a commercial instruments or probe, so I can't calibrate this little gauge, but at least I have some raw idea of the voltage level. This method has many advantages as safety measure, because no direct connection to the high voltage side, no high voltage resistors needed, and works for AC or pulsed DC. And finally, a short conclusion. In this project, I built a simple yet effective variable high voltage power supply using affordable components, offering precise control for high voltage experiments. Tune the frequency, duty cycle or input voltage to achieve the desired output, making this device a versatile tool for any electronics enthusiasts. And safety note, please do not attempt to recreate the experiments shown on this video unless you are familiar with high voltage safety techniques. Direct current, even above 60 volts, may be lethal even when the AC supply voltage has been disconnected due to the stored energy in the capacitors. I have no responsibility on any hazards caused by this circuit. Be very careful.